All right, we are in AP Calculus. Today's date is Thursday, October 24th, 2019. We are talking about tangent line approximations. Objective, someone read it.
Use a tangent line to approximate values and determine if it is and underestimate or overestimate.
So it's the same objective as yesterday in terms of right here to the left. And then we have this additional objective of determining whether it's an under or over estimate. All right, so another reader, either Stego or Arrow, talk about what happened at my hometown.
I think I remember this one. Maybe.
Okay.
18 inches of snow fell on the first day of a terrible snowstorm in Mrs. Snell's hometown of Colfax, California. At the end of the first day, snow continued to fall and rained 12 inches per day.
All right, so let's analyze what information is given to us, and then we're going to go and actually start answering a tangent line approximation question. So just analyzing, what did it give us?
So the first time it was 18 inches.
First day was 18 inches. So how do I say that? Let's make a function. Let's what should our function letter be? Should we do S for snow, or should we do F for fall, or
F for first day?
well, we're going to say something of 1. That'll be the first day. We have to choose a letter out here though for a function. You want to just do S for snow?
Yes.
All right, so we're going to say S, and then on the first day, so S of 1 means the first day. If I put S of 2, that's the second day. S of 3 is the third day. On the first day, I got 18 inches. And what is this telling us? At a rate of 12 inches per 1 day. Great.
That's the slope.
That's the slope. And then how do I do the notation for that, Gio?
This is F prime.
S prime, yeah.
Oh.
Or you said F prime? Yeah. So S prime, take the derivative of whatever function I was talking about, and it's S prime of what, Stego? S prime of 1. And S prime of 1 is what, Arrow?
Is it 12?
It is indeed 12. Nice. So already we can start answering like what the equation to the line tangent is. So let's go ahead and find the equation to the line tangent, and then we'll use that to approximate 1.2 down here. So give me the general formula, Stego.
Y, the one with addition?
Yep.
Y minus box equals box, and then the parentheses x.
There it is. All right, either Geo or Arrow, tell me what I can put in here.
So you can do y. Wait, it should be the slope. F prime should be 12.
So slope is 12, all right, so slope is 12. And then Arrow, what's the other piece of information we have?
You have both the x and y values.
So what is X?
X is 1, y is 18.
Yep, and that's something that I should have talked about a little bit more yesterday. Whenever I have some function, I'm going to do a general function down here because we're already done with this first part. If I have like f of 2 is equal to 5, this is totally unrelated to this problem. Maybe I should write this over to the side. But if I have something that looks like this inside the parentheses is the x, and the outside is the y coordinate. So whenever you see something in the parentheses, they're talking about the x coordinate or the input, and then what it's equal to is the output, usually the y. So just from S of 1 is equal to 18, Arrow is able to tell us 1 is x and 18 is y. So far so good? All right, so now we're actually going to use this equation that we found to approximate how much snow there is at 1.2 days. So I'm going to rewrite the same formula that we had from up above. So I'm going to rewrite y minus 18 is equal to 12 times, and then in the space of x, leave a blank, minus 1. What am I going to substitute in for x now?
1.2.
1.2. So let's write it down. We're doing 1.2 now. We're using this equation, and in the place of x, we're plugging in 1.2, and then we actually have to calculate that. So 1.2, mental math here. 1.2 minus 1 is, shout it out,
0.2.
0.2. Now 0.2 times 12 is?
1.4.
Not quite. Again, you can do it off to the side if you want. Not quite.
Wait.
0.2 times 12, 2 times 12, and then move the decimal place.
Oh, 6.
2 times 12.
What?
4.
2 times 12.
Oh,
4.
24.
24. Now move the decimal place
2.4.
once. 2.4. All right.
Ah.
So this thing right here is 2.4, and you can maybe draw that up above. This thing is 2.4. And then I need to add 18 to both sides, so my final answer is
Doesn't it mean 20.4?
20.4. There it is. And I guess if we're being very technical, we are now approximating, so y is approximately equal to 2.4. But we don't need to be technical when it comes to AP Calculus, but you guys can do a wavy sign here if you want. An approximately equal to sign. All right, so what's happening in terms of a graph? So in terms of a graph, we don't know exactly what's happening, but we know at time is equal to 1, what's happening?
It's 18.
It comes up here to 18, so go ahead and make a point up here at 18, which is right about there. And we also know that we have a positive slope at that point. Why do I know that? Why do I know I have a positive slope at this point?
Because you're assuming, because before that day was 0, right?
That might not be true. What if it was 0, but then it was starting to decrease, it was starting to melt? There's something up here that tells me that the slope is positive. The rate is slope, and the rate is positive. This 12 is a positive number. This is saying the slope is a positive 12, so I should have right here a slope of 12, which means I don't know what's happening over here. I'm guessing I started at 0. I don't know what happens, but somehow I have a positive slope. So my slope is somehow positive, and we're going to say it's 12. So I don't know how to approximate that. We're going by 0.2 and 5, so I'm going to guess something that looks like that. Okay, so that's all we know, and in fact, I'm just going to kind of approximate it a little bit more like that. So we know that we have some sort of positive slope. Let's jump down here to the next bit of information. So it's saying when t is between 1 and 1.2, so between here, and between 1 and 1.2, s double prime of t is greater than 0. S double prime of t is greater than 0. What is that saying? What information is that giving us? Concavity. The concavity is up or down?
Up.
So write it down above this. This is saying it's concave up on that interval between 1 and 1.2, which means I can now add more information to the graph. Instead of having this blue line back here, you can leave it. I'm going to go ahead and change it. Not only do I have a slope at this immediate instant that is 12, but it's also somehow concave up. But notice that when we made our graph so it does have that original slope right here. So what I really have happening here, and I can go like this. This blue line was the line that we used to approximate 1.2. So on this blue line, we found about 1.2 is 20.4 on the blue line. But it's saying, hey, this was actually concave up. It's actually more like the red line. You should be more concave up. Are we okay with what that's saying so far? Ask questions now. Yeah, so this red line right now is using this new information saying, hey, on this interval over here, I'm somehow concave up. Somehow increasing at an increasing rate. But we use this blue line down here when we were using the tangent line approximation. Tangent line approximation is some line, not a curve. So when we found 20.4, that 20.4 was on this blue line. So now I'm going to ask you, was this point on the blue line, was that an under approximation or an over approximation? And compare it to the red line. Is it above or below? It's an under approximation.
Why?
And that's the question.
The other line.
It's under the red line.
Yeah.
We're going to talk about it in depth in a sec, because I'm going to talk about underestimate versus overestimate, or overestimate versus underestimate on the next side. But just saying this again, this point on the blue line was the point that we found right here. 20.4 was the height at 1.2. So I went over 1.2 and I got 20.4 roughly.
So it's just because the red line is not going through it?
So because the red line is above this point,
Okay.
this point is an under approximation because it's under the red line. So far, so good. Arrow good.
Yeah.
Psycho good. Geo now gets it. All right, so let's go to the back. The difference between an overestimate and an underestimate, I keep saying it backwards, but it's fine. So let's say I have a graph that is completely concave down. Let's go ahead and say that we draw a slope over here on the left-hand side. So everyone draw the slope with me. There's a slope. If I draw the slope at that point to the left, actually, sorry, to the left of this line right here, and you're always drawing it on the line, never on the curve. You're always using the tangent line approximation. So this point to the left, is that an over approximation or an under approximation?
Over approximation.
Oh, interesting. So let's go ahead and do an arrow and say that one is an over. We'll just say over. We don't have to say over approximate because we're saying approximate over and over again. What about this line to the right? Is that an over approximation or an under approximation?
Over.
Interesting. That's also an over approximation. Take a guess before you do it. Do you think you're going to have an over approximation or an under approximation on the right side?
Over.
Think over?
Yeah.
Geo? Over? Let's try it. So let's go ahead and make a slope. I need to get better at drawing the slope of the line tangent. So when I'm on the line that's tangent to the graph, am I over approximation or under when I'm to the left? That one's also over. And the right one is also over. So the main thing to take away from this exercise is when I have something that is concave down, it doesn't matter where I am, to the left or to the right, positive slope or negative slope. The only thing that matters is the fact that it was concave down. So this, make it red, make it super giant because it's very important. If concave down, and what's the definition of concave down again? F double prime less than 0. Then you will always, always, always be what type of approximation? Then overestimate. Or you can say an over approximation. The key word being over. All right, so take a guess before you even do it. When I come over here and do the blue line, do you think you're going to have an over approximation or an under approximation? Geostego? It is under. And you can see that because go ahead and draw a line, draw a slope that's tangent. And maybe I should actually use the line tool. Maybe that would save my embarrassment. If I do this line really big, there it is. And then I do another line over here. You can see that our tangent line approximation, no matter where I am, as long as I'm on the tangent line approximation, I am always going to be under the curve because this is now concave up. So it's kind of like the opposite. If I'm concave down, you always think of down as negative, then I'm overestimate, which I kind of think as positive. So you kind of think of it as the opposites as long as you're comparing it to the second derivative. So again, I'm going to write it in words, and you should as well. These were all under, 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 and under. And when I say under, I'm saying under the actual curve, under this blue concave up curve. So the way that I say this in words is if concave up. Geo, give me the definition of concave up.
F double prime greater than 0.
There it is. If I'm concave up, then I have an underestimate or an under approximation. They're both the same word. You can use them interchangeably. Interchangeably, that's how you say that word. What's going on? Underestimate. Or you can say under approximation. And underline the word under because that's the important word. All right, we think we're good?
Yeah.
So on the homework, not only are you going to be doing overestimate or underestimate, but you're also going to be trying to make this graph for every single problem. Well, I think for the front half of the problems. I'm not exactly sure.
Can you print the
I will also print you out the homework.
I know.
All right, no more questions? All right, then you can begin the homework. All right, so let's do number 1 together. So we know that the x-coordinate here is 0, the y-coordinate is 1, and we also have this derivative. So we need to use the tangent line approximation to find x at 0, or to find x at 0.1 for our approximation. So first, we're doing our tangent line approximation, so immediately I write y minus box is equal to box times the quantity of x minus box. All right, we have our x and y coordinates. Shout them out.
Y is 1.
Y is 1 and x is
0.
0. We have f prime of x, but we haven't plugged in the x. So let's plug in the x. If I plug in x, what is our x? 0. So 3 times 0 is,
0.
and then minus 2 is,
-2.
that means our f prime of 0 is -2. So I come down here and say, okay, -2 is a number that I plug in for the slope. And now I'm using this thing to approximate f of 1, or 0.1. So come down here and I'm going to say y minus 1 is equal to -2 times the quantity of x, not x. I'm substituting in 0.1, so 0.1 minus 0, which is just like that. Then I have to do some mental math. -2 times 0.1 is
0.1. 0.2.
0.2, and that's being set equal to y minus 1. I add 1 to both sides, and I get y is equal to...
Wait, isn't it negative? Oh, yeah. Negative, wait, just
Wait, why do we have to solve
0.8.
it? Why can't we just leave it?
because you need to give an approximation for f of
0.8.
0.8. So that's one of the answers. But then it goes on and says, all right, we also know that f double prime of x, what is it talking about here? F double prime of x is concavity. It says the concavity is positive, so it's concave up for that interval that we were looking at. So then it asks, is that approximation greater or less than? We need to not only explain our reasoning, but also include the sketch of the curve of the tangent line. So let me actually redo that, Command-Shift-C. So if it's concave up, so we say it's concave up, therefore it's going to be an under or over approximation.
Under.
So we're going to say down here, yeah, down here is fine. We're going to say under approximation. And why? Because f double prime
It's concave up.
is greater than 0. Or you can say f double prime of x, if you want to be a little bit more precise, is greater than 0 on that interval. But that's fine. So that's our second part. And our third part is going to be our graph. So now we need to sketch out a graph over here. So let me draw some quick axes. And I'm talking about the point 0, 1. So I can just go like this. So I'm going to say 0, 1 lives right about here. So I'm going to say that point is 0, 1, if you're interested in what that point is. And I also know that over here I'm going to have, okay, this is not going to be to scale, but I'm going to kind of enlarge it. This is going to be the x-coordinate 0.1 or 0.1. At 0.1, I got 0.8. So down here, I'm going to say this is right here. This is my coordinate 0.1, 0.8.
Wait.
What's up, Joe?
How do you got that dot in the zero? The first dot right there.
0, 1?
Yeah.
This is telling me right here that the x-coordinate is 0, so don't move in the x-coordinate. And then the y-coordinate is 1, so it has a height of 1. So right here, f of 0 equals 1 means I have a point right here.
And then a 1.1 have a height of 8. That's supposed to be up more.
So which is higher, 1 or 0.8?
Oh, you're right. Never mind.
Yeah, so 0.8 should be a little bit down. But we also know some more information. We know that it's concave up at this point. So even though we have a negative slope, we are concave up. So how do I have a negative slope yet concave up? And I basically just drew it right there. I have a negative slope, but I'm concave up. So you should have something that looks like that at this point. So at this point, I'm going to come and use a different color. At this point, I'm concave up, but I know that my slope was purely just a negative slope, and I have to do a line here. So it doesn't matter what the exact slope. I mean, it would be nice if I could give an exact slope of -2, but I mean, this isn't drawn to scale anyway, so it doesn't really matter. So this is what's actually happening in this problem. I have a negative slope and something that's concave up. Those are the only two things I care about. Sign of the slope, sign of the concavity, or concave up or concave down. Once you have that, it's very clear that if I'm on this point, I guess it should be a little bit off, but anywhere here and here, I'm going to be concave down. Or it's not concave down, it's an under approximation because I'm going to be under this curve. All right. I guess if I'm being very technical about this, I could draw it slightly differently. So that is perfectly fine, and I could maybe freeze the screen. I want to be very technically precise in the video, so I'm going to redo this really quickly. While I do have the point here at 0.1, 0.8, so this is still 0.1, 0.8. What's actually happening in this graph is this whole interval between 0 and 0.1 is the thing that's concave up. So we approximated our line right here. So our line should look like this, where it goes through both of these 2 points. And then from there, I know that it's concave down at this point right here. It's concave down between here and here, or sorry, concave up between here and here. So I should have something that looks like this. So it has a negative slope, but it's concave. It should only have a negative slope, but yet concave up. I'm trying. It's hard. That's the best I can do. No, it's not. Whatever. I still have a negative slope, but I'm concave up. Therefore, this point right here is under the point of my curve. So this is a more technically correct drawing. Because this is more correct because this line is going through both of these 2 points, because we have a line that's going through 0, 1 to approximate 0.1, 0.8. So that's where my point actually exists. And then from there, this whole interval is concave up. You can see that this blue point is an under approximation because it's under the red line. Okay. All right, you think you guys are going to be good with number 2 and from here on out?
Yes.
All right.
Can you go to the restroom?